For generations, our world has challenged explorers to seek what lies beyond the horizon. Now, the invention of spaceflight is leading us outward to explore a host of alien worlds with vast new territories. Today, we see the sun, moon, and planets with penetrating clarity through the eyes of the intrepid machines blazing a trail for us across the solar system. Their cameras have become our windows onto a bold new adventure. Their discoveries have become our cosmic vistas. Since the dawn of humanity, the night sky has been our window onto a larger reality. For our ancient ancestors, the heavens above were evidence that there is something out there. Out of reach, yet somehow connected to life on Earth. As they gazed upward from night to night and year to year, our ancestors noticed changes in the sky and wondered what those changes might foretell about their own destinies. Some of those changes were easy to spot, like the nightly drift of the constellations from east to west. Or the monthly spectacle of the moon marching through its phases. And there were more fleeting changes, like colorful displays of aurora borealis. Or the chance appearance of a bright comet slicing across the heavens. But no change attracted as much attention from our ancestors as the complex dance of a few brilliant objects moving around among the constellations. They looked like stars, but by their motions it was clear these objects were somehow different. They were called the wanderers, or in Greek, the planets. For centuries, astronomers puzzled over the motions of these planets, trying to decipher the clockwork nature of our universe. But it would take the invention of the telescope to show us how special the planets really are. When the telescope arrived, it offered a new kind of window on the universe, one that transformed the planets from lights moving in the sky into distant worlds orbiting around the sun. In other words, the telescope helped us understand that we are part of a solar system full of planets, asteroids, comets, and more. But there is also a limit to how much of the solar system any telescope can show us. Which is why what happened next was the most exciting development of all.
CMO.
Loaded and verified.
Roger, thank you. Will you transfer to the enable queue? Copy that.
Roger.
In the 1960s, a new kind of technology appeared that was destined to show us the planets like never before. Thanks to spaceflight, it was no longer going to be a matter of getting better windows on the distant planets. Now our windows were moving to the planets and giving scientists back on Earth a taste of what it would be like to visit alien worlds. The earliest space voyages to reach beyond Earth were aimed at our nearest neighbor, the Moon. And when a Soviet space probe named Luna 3 became the first to image the Moon's hidden far side, it was clear a new age of exploration had begun.
5, 4, 3, 2, 1. Fire command, fire command.
Suddenly, every planet was a potential destination. Before long, space probes were crossing the great ocean of interplanetary space and sending back their close-up glimpses of Mars, Venus, and the sun-baked surface of Mercury. By the 1970s and 80s, the US space agency, NASA, was ready to reach even farther, to the distant outer planets. The most celebrated mission of this time, Voyager 2, managed to visit 4 giant planets in a row, including Jupiter, Saturn, and Uranus, before finally reaching Neptune in 1989. More recently, a second wave of missions has given us powerful new views of many of the planets and allowed us to see the solar system from a fresh perspective. In some cases, that perspective means more detail and more complexity than we could ever have dreamed of. Like the detail in these cloudy swirls in Jupiter's turbulent atmosphere. Or these broken and refrozen icebergs on the surface of Jupiter's moon, Europa. In other cases, spacecraft have revealed more history than we could ever have hoped for. Here, in a crater punched into the barren Martian desert, we find ancient layers of rock jutting from the crater's rim. Geologists have read these layers like the pages of a novel, and the story they tell speaks of long-vanished water that once bathed an alien landscape. Collectively, the rich new views and precious data that are coming to us from so many planetary missions make it clear our solar system features astonishing diversity. Yet the evidence is also telling us these very different places in the solar system have a common origin. According to the best available evidence, some 4.5 billion years ago, our sun was born out of a vast cloud of interstellar gas and dust. Today, the Hubble Space Telescope can see the same process at work throughout our Milky Way galaxy. What appears to us as a gorgeous nebula of glowing gas is really a star factory, and our sun came into being in just such a place. But the sun was not created in isolation. As matter swirled together to form our newborn star, a small fraction of that matter ended up in a disk of gas and debris spinning around the infant sun. As material in the disk coalesced, it formed planets, moons, asteroids, and comets. And like different children born to the same parents, each member of our solar system family has its own distinct characteristics. One of the big questions to come out of planetary science is how could all of these solar system objects have started from the same basic ingredients, but followed such very different pathways? As far as we know, only one of those pathways led to Earth, a planet capable of supporting life and keeping that life well protected for the billions of years it took for us to finally show up and start wondering about the solar system. The poet T.S. Eliot wrote, "We shall not cease from exploration. And the end of our exploring will be to arrive where we started and know the place for the first time." When it comes to exploring the solar system, Eliot's words are literally true. Every planet, every moon, every asteroid we visit has a different story to tell us. And by putting together all those stories, scientists hope to understand how we came to be here, in our place, in our time. These are questions that touch us all, and the journey to answer them has now begun. Of all the destinations that await explorers in our solar system, none could be more terrifying or more beautiful in its alien grandeur than this hellish domain of searing, writhing, and dancing fire. This is the vast and volatile powerhouse whose explosive outbursts can reach across millions of kilometers of space to rattle our tiny planet. But it is also the fountain of creation, upon whose energy our entire living world and civilization critically depend. It is our sun. Even in ancient times, our ancestors understood that without the sun's warmth and light, life as they knew it would not exist. For them, the sun was nothing less than a god. Today, we know the sun is a star, just one among the hundreds of billions that populate our Milky Way galaxy. But for us, the sun is special. In our solar system, there are 8 planets, several dozen moons, hundreds of thousands of asteroids, and possibly trillions of comets. But there's only one sun, and it's 1,000 times more massive than all the rest of the solar system combined. The gravitational pull of all that mass is what keeps everything in its orbit. So no matter where you are in the solar system, it's the sun that takes center stage. 4 centuries ago, the astronomer Galileo was certain the sun, not the Earth, was at the center of our solar system. He would later be tried for heresy for defending this radical idea. Galileo was also one of the first to point a telescope at the sun, which led him to another surprising discovery: sunspots. These are dark patches that appear on the sun from time to time and seem to drift across its blazing surface. In time, astronomers discovered that a subtle pattern governs the appearance of sunspots. Over a cycle lasting approximately 11 years, they grow increasingly more numerous on both sides of the sun's equator, spreading northward and southward until they cover all regions of the solar surface. And then, just as they reach their peak, they diminish, and the cycle begins anew. Sunspots offer a visible clue that the sun is not just our cosmic light bulb, but a complex and dynamic system. Even before Galileo's time, there were clues that there is more to the sun than meets the eye. The most obvious appears every time the moon passes directly in front of the sun, causing a total eclipse. This wispy white glow that stretches outward from the eclipsed sun is called the solar corona. It is the sun's searingly hot outer atmosphere, a region where ionized gas is energized to a temperature that is far higher than at the sun's surface. And like sunspots, the corona is always changing. These clues suggest that the sun releases its energy in complicated ways. But for generations, scientists were stumped trying to understand where that energy comes from in the first place. Then came the atomic age, with an unexpected side effect. The discovery of nature's hidden nuclear forces gave scientists the insight they needed to understand what makes the sun shine. Like most stars in the universe, the sun is mainly made of hydrogen gas. At the sun's surface, that gas is about 5,600 degrees Celsius, hot enough to glow with a bright yellowish light. But deep inside the sun's core, the temperature rises to millions of degrees. And under these extreme conditions, hydrogen atoms can combine to form helium. The energy released in this reaction gradually works its way outward from the sun's core through overlying layers until it is released into space. Only a tiny fraction of the sun's total energy falls onto our world, but over the eons, it has been remarkably steady. And this has allowed life to evolve and flourish on Earth. Yet there are also plenty of reminders that the sun is not always so benevolent. Scientists have long known about giant explosions on the sun called solar flares that can wreak havoc with power and communication systems while producing dazzling displays of aurora borealis. To better understand the sun's changeable nature and its influence on Earth, scientists have learned that they must venture into space, where the sun can be monitored around the clock and observed in ways that are not possible from the ground. This has allowed astronomers to study the way features shift and change on the sun's rotating surface over a long period of time. A less direct way of studying solar activity from space involves using a circular disk to block the sun's light. This creates an artificial eclipse inside the spacecraft, making it easier to follow dramatic changes in the sun's corona. For years, the SOHO spacecraft has made good use of this method. Here, SOHO looks on as a comet swoops in near the sun and is greeted with a blast of high-energy particles. In some cases, a vigilant spacecraft can even catch the occasional trespasser. Here we see the planet Mercury transiting across the sun's fiery disk. These views from space reveal an incredibly dynamic sun, intimately connected from surface to corona by a powerful but invisible force: the force of magnetism. In fact, the sun is the most powerfully magnetized object in the solar system. The reason for this is that the sun is not a solid body, but a turbulent, electrically charged fluid. It is the motions of that fluid that ultimately generate the sun's tangled and ever-changing magnetic field. This field frequently pokes through the solar surface and forms long loops out into space. The bases of these loops are where we find sunspots, because that's where material that would normally be turning over and sinking back down into the sun's interior is temporarily held at the surface and allowed to cool and darken. The loops and twists in the sun's magnetic field can store vast quantities of energy. Occasionally, that energy is released with astonishing speed and violence. The result is a solar flare. On October 29, 2003, SOHO captured these views of one of the most powerful solar flares in history. It begins with a large, magnetically active region rolling into view on the sun's left-hand side. As the sun rotates, the region gradually moves to the center, where it faces the spacecraft and us. With a sudden flash, the flare erupts, followed by a burst of static as high-speed solar particles pummel SOHO's camera. SOHO survived, but a powerful solar flare like this can easily knock a satellite out of commission. Another hazard often associated with solar flares is a coronal mass ejection. It begins as a huge release of magnetically energized particles from the sun's corona. The particles shoot across space at high speed. When they encounter Earth, the particles cascade down onto the atmosphere, producing brilliant aurora around the North and South poles. What the age of space exploration has taught us is that the sun is not an isolated and distant part of our solar system. Rather, the sun is an environment that Earth travels through. And it's not just Earth that experiences this. The sun's magnetic fields and the flow of particles that stream off its surface travel well beyond our world and all the other planets of our solar system. It ultimately creates a giant bubble that separates all of us from the flow of interstellar material that permeates the galaxy. With the sun, we not only live with a star, we live within one. Billions of years ago, each planet formed from the same primitive mix of atoms that went into creating the sun. Since then, the planets have all gone their separate ways, each with its own unique story to tell. But there is also an underlying connection, because in the end, we are all children of the sun.